Hello, 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 hello. How we doing? Something a little bit different today. Let's get my chair sorted. The green screen's gone a bit funny. Oh, hello. Oh no, oh, good. Right. Yeah, I'm going to give you a bit of a taste for what I do at work, which is a bit weird because I'm off work this week. But I'm going to give you a bit of a yeah. I don't know why I'm doing this when I'm off work. I do know why I'm doing this off work because I'm getting it sent to China for manufacturing, and I've got a board that I've already sent to them, um, and I might as well get this one done and dusted, and then they can be posted together. It saves on postage, so not a big fan. Would much rather get things made here in the UK. But I got a quote from for the last circuit board I've designed that they're currently making at the moment. In the UK, 384 quid for one board plus that plus delivery, all that stuff. Get it done in China, $5 plus $25 shipping. I mean, for 5 boards, like, it's just stupid. For hobbyist stuff, at least, anyway. This is work, but it's bracketed under the same thing, really, because it's small little prototype boards. What I need to do, really, is share my screen with you so you can see. That'd be a good idea, wouldn't it? Center screen. Here we go. So the software we're using. Hang on a minute. Hang on. Why is that there? I want that there. Hey, there we go. Right. So yeah, the software I'm using is Eagle. As you can see here in the top, if you engage squint mode, PCB design software. So for anyone who's not seen it before, you draw it up as an electrical schematic in this, and then you flip over to the board, and then you can place the components on the board. So it's a two-stage process. You don't draw the board straight out. There are softwares where you can do that, but I'm not going to be doing that today. So I'm going to use the command add Bosch, and up we get a list of devices that are in the Eagle library. You can add to the library. I'm going to hopefully not need to do that, but we'll see as that goes on. And what's the board we're going to do? That'd be useful to know, wouldn't it? So we develop supercapacitors at Loughborough University, and we want to be able to test them. They've got quite a wide voltage window compared to the ones you buy off the shelf. The ones you buy off the shelf, in fact, I'll go and grab one so you can see what it looks like. So here's a few that I bought from Batlin in their closing down sale, just because I saw them and thought, why the hell not? This is actually 2 Supercaps in there. You can see the 2 of them. Will it focus? Maybe. So there's 2 just bundled up into one package with the dual leads on. And as you can see here, that's 2.5 farads at 5 volts. Won't focus, you blasted thing. No, whatever. Take my word for it. It's 2.5 farads, 5 volts, and that's for a dual cap, non-balance. So these could technically run away from each other. I.e., when you charge one, you could get one charged up to 5 volts and the other one at 0, which would actually overcharge them. Because what this is this is 2 caps in series. So each rated at 2.5 volts. In fact, I can see on them 2.7. So in theory, you could push this to 5.4 volts. But the risk there, of course, is that you could end up with one of them at 0 and the other one at 5 volts, and that would it would have blown before that because they're not balanced. But because these are sold in a packet, they probably are matched, so the chance of that is reduced, but still exists. But anyway, our ones that we do go somewhere between 6 and 8 volts for a single cap. thinking if I've got some of those to show you. Bear with me 2 secs. So this isn't in the style we make them anymore, but this is just in like a petri dish type thing. The cap is actually the layer that's printed on here or painted on here, and that's a wide voltage window. Not much to look at. Clearly that is not a production ready thing. You would print, and what we do now actually is we print them onto sort of like caps on tape, rather than it being in this solid glass jar. And then the idea is that with that is you roll it up into a tube, shove the tube in a case, and then you get something that looks like that. Obviously in research we're not really focused on production, not for our projects anyway. So it's just making a device that works, so we can paint it on glass, it doesn't matter. So that's an example. I've got some better ones at work, but I haven't got them with me here. Thought I had one upstairs. I probably have got one upstairs, but I can't find it. So, wide voltage range. That's pretty much a linear discharge curve. So if you've got voltage here and you've got time along here, assuming you're pulling a constant current, the voltage will drop reasonably linearly. Supercaps, that's not strictly true, but it's certainly a lot more linear than a lithium-ion battery, which if I draw you a graph, that is sort of, you know, as a sketch, a lithium battery discharge curve. It's very, very flat, and then it suddenly tails off, and it's at this point you start doing damage to it. So that's what we call a deep discharge. So that's why you don't discharge them below, you know, 2.5 volts or whatever you choose to set as your minimum. 2.7 some people do, but yeah, whatever, it doesn't matter. And it does depend on the cell chemistry as well. So lithium ion, i.e. as in LiFe, LiFe batteries are slightly different. There's also lithium manganese, cobalt, and they're all ever so slightly different. So a capacitor is more like that, a straight line, more linear as we call it. What's she doing? Pippa! Oh, God. Ignore it, it'll go away. So that's no good. If we want to power a string of LED fairy lights, for example, or whatever, you need a constant voltage, because you don't want the brightness tailing off, because as soon as you get to this point, they're not, the LEDs aren't going to light, for example, you know, arbitrary scale on here. So you need to boost the voltage when it gets low, but you may need to buck the voltage, i.e. reduce the voltage when it's quite high. So the output needs to be a reasonably stable voltage. So we need some sort of buck boost converter, so we can squeeze all the voltage out of the cap and therefore all of the energy. Now, unlike a lithium battery, we can discharge it all the way down to 0. A cap doesn't care about going to 0. In fact, some of them will even go negative, but you're not getting extra energy out of that. You can't overcharge them because they will go pop, but we can discharge them down to 0. So we want to get every last bit. So the buck boost regulator needs to have what's called a dropout voltage as low as possible. So it stops working at, let's say 0.1 volts. That would be great because that means we can go all the way down to 0.1 volts on the cap, and then the boost converter stops working and we can't get any more out. If I had a dropout voltage of 5 volts, say, and we've got the cap charged to 8, we can get all the way down to 5 and then it stops working. Cap's fine, but the buck boost converter isn't. So we need one with a very low dropout voltage. And of course high efficiency, because we're going to get losses here. So we can't, unlike just direct driving the LEDs, we are going to lose some energy in having this system. But it is worth it because we can operate the LEDs on a cap that would ordinarily be too low or too high for the LEDs. So having a guess here at some analog devices, would probably be better actually going onto Linear's website. Well, analog now, isn't it? They've been bought out. But what I'm looking for, LTC, they're pretty expensive compared to others. They've all just gone completely out of my head now. Microchip and Texas and all that lot, TI, in Texas Instruments. But they are pretty decent spec. In fact, okay, right, no, let's do that. Let's not fart about. Let's go to Linear Technology, which will now put us through onto the analog website. Yeah, it does. Whatever, go away cookies. No one likes you. Products. Okay, so power management. We want. They do Supercap stuff. The problem with the commercial Supercap chip is that they aren't designed exactly for that, commercial Supercap, which are 2.5 to 2.7 volts. That's no good for our stuff because we want to push them up to, getting on for 8 volts for our in-house made ones. So it means we can't use the off-the-shelf stuff. Really irritating, but these companies are market driven and there isn't a market for 8-volt caps at the moment because they're not in production. We've only just discovered them in the last sort of couple of years, so it's going to be a good 5-10 years before they hit the shelves. As is the typical flow of information from academia to industry and so on. So I want a standard. We could just use a low dropout linear reg, but it would need to be buck boost, and I don't think there are any. Sepic would be nice, so we'll open a tab for that, and buck boost would be nice. Now, if they've got a micro module one, these things are pretty cool. They're a bitch to solder if they're in a ball grid array. Let's have a look. Yeah, that's a BGA package. I really don't even want to entertain the idea of doing a BGA. Do you want your mouse? Well, go and get it then. You normally play fetch. That's a BGA. I don't want a BGA. These are all going to be BGAs because they're all the same. LTM80s. Let's try the LTM46s. That's a BGA as well. Right, I don't want a ball grid array. Internal power. So these will be slightly lower efficiency than external, slightly less configurable words. But it's just a single package to solder, so that might be. So we've got these different parts. The deal, we've got loads. Right, okay. V out typical. V out min. Sorry, I was reading that thinking that's a really weird typical voltage. Obviously, if you're watching this and you're in the know, I'm all open to ideas. Let me just smash the coffee down. Right, okay, so V in. Now, we could do these in series, right? And one of the things I would like to be able to do on this board is have the ability to put caps in series or caps in parallel. Caps in parallel is easy, because you actually just shove them all into the same terminal block, or we can just put multiple terminal blocks. Series is more difficult because it's going to up your voltage. So this needs to be a little bit tolerant. And of course, we need to then balance the cells. Now, we can do that in a quick, dirty way. You know what I'm going to do, don't you? Here we go. Right. Right, so. Eagle, why don't I do it in Eagle? You. Anyway, so if we've got our. Bad stuff. Right, pencil. We've got our cap here, and so we've got two of them in series, right? And these go off to our load. Right, we'll just draw a resistor. Okay, and then we're going to have some sort of charge circuit. Let's put a switch on here. Hello, Pippa. Yeah, meow. And let's just put some sort of current source in here. Boshty boshty bosh. So this is just a really, really crude, let's charge our supercap. Now, if these are for 2.7 volt tolerant, if we're using a commercial one, if we're using our own, they're maybe up to 8 volt tolerant. Yeah, 6 to 8, but let's say 8. We certainly don't want to go above 8 because the things start breaking down. We might want to for research purposes so we can actually analyse the breakdown. So let's say 10 volts is going to be our upper window per cap. So we could have 20 volts across here. What we need to ensure is the voltage across here is the same as the voltage across here. Okay. Think about what I've said there. We need to ensure the voltage across those two caps is the same. That's not equivalent to saying I want that to be 2.5 volts max and that to be 2.5 volts max or 6 or whatever. I want them to be the same. So if we put in a 2.5 volt tolerant cap, I want it to be 2.5 volt max. If I put in an 8 volt cap, I want it to be 8 volt max. So it needs to be, there needs to be some sort of dynamic ability here to balance the two cells. Now, if we were going to do it really, really crude, right, ignore what I've just said there and say we want to make sure these don't go above 2.5 volts. What we can do, and this is really naughty, but it works, and you can't deny it works, just a little bit naughty, is we can put a Xena diode, whatever you want to call it, rated at 2.5, right? Excuse me drawing on paint here, but yeah, whatever. Or to actually draw it properly. 2V5, 2.5 volts. So that means, so this is in reverse polarity, so it doesn't exist. So we charge up, we go from 0 volts, this is volts on here. We charge up, all nice and linear. We hit 2.5, okay? And then the breakdown voltage of the Zener is then hit. And what happens now is this Xena starts conducting backwards. Okay, so it breaks down, and for argument's sake, let's just say it's short. It turns into a short circuit. That's not strictly true, but let's say it turns into a short circuit. So it shorts this cap out. Okay, so the voltage across the cap, if it is shorted, theoretically, goes to 0. Yeah. In that immediate time step, yeah, that one snippet in time, that one femtosecond, this shorts. Doesn't happen like that because it's not a solid cliff, but let's say it just makes it easier to deal with, right? Now what's happened? Well, we're actually below the breakdown voltage now. So this suddenly isn't a short and it's a diode again. And because there's not been enough time for the cap to discharge itself through this circuit, this circuit here, right, there is still charge remaining on these plates. Okay, so we still have a plus and a minus here, going off conventional electronics. So that means this, you can see this is a battery. It still has charge on it. So, because this circuit is now open circuit here, this voltage is actually, let's say, just short of 2.5 volts. Because it might have just discharged a little bit or sagged a little bit. We'll talk about that later. So the voltage recovers. Okay, and we're now up here. Now, if we're still charging, this is going to come back up and do the same thing. Like that. And effectively what will happen is this will just happen really, really, really quick. In reality, it will actually, it will transition, so it will just level off, and this will just be a value resistor, high value resistor. But for argument's sake, let's stick with this analogy. So what have we achieved in doing this? Well, by sticking that across there, that cap can never go above 2.5 volts. So we have now protected that cap. We're still charging. If this second cap, say it doesn't matter which, the second cap is only at 1 volt, well, this hasn't met its breakdown. So the current flow will actually go through here, through there, down and back onto the cap, and it will charge this up until a point occurs where both of them are at 2.5 volts. Both these Zenas are breaking down, and the current flow is through the Zenas and back through. Okay? And what will happen is we'll get a huge current spike at that point, and we can then turn off. I'm pointing at the screen with my finger, right? And we can then turn off this switch, and these two caps are charged. These Zenas, well, we can't discharge through them. There's no circuit. They're not breaking down. So the caps will remain fully charged at 2.5 volt. There will be a little bit of leakage and they will gradually self-discharge, but we'll assume for now that time is infinite. If we open the switch, so what I should have done is gone whoop like that and gone switch. So now if we close this switch here, we can then drive the load with these two. The voltage on these two caps, the total voltage will be 5 volts, and these will discharge then through the load. It's always going to be below 2.5 volts per cap. So it's not strictly true, but it will be. And we can then power the load until the point that we want to recharge it, and then we go through the whole process again. So that is the quick and dirty method. There are other ways. You can put comparators on here. That's probably the more preferred way, and have balancing leads. So you actually would charge through a switch and actually inject charge into this point. So you can then balance cells. So you could, well, you wouldn't do this because it's pointless. but say you had another cap in there, and you could charge a specific cell, and you have some sort of microcontroller here controlling these two switches. So then you can see that you can feed current directly into this cap, and at that point you don't need these either. Right, so before paint gets too messy, in fact no. So that's the quick and dirty method. That is the preferred method, but considerably more complex. Much more complex, and that's what the specific supercap chargers that you can buy will do. But of course, they're designed for commercial supercaps. Very different voltage window from what we're operating on. So we're going to have to think about that. The other way, and the even more crude way, is to just not care and risk it. Sounds fun, doesn't it? Ha. That's probably what we will end up doing. And I'll explain for why. Simply because we're going to be plugging these supercaps into a terminal block. These aren't going to be soldered onto the board. So, because we're going to be testing lots of different devices, so that gives me the ability to plug in an external balancer to a separate balancing module, which ensures that the caps are balanced, but it does that on a separate circuit that just happens, we cram the wires into the same terminal block. That would be more preferred because it keeps things modular, it keeps this circuit simple, so when I inevitably have a problem with this board because I've, cocked it up, it's a much easier task to modify the board so that it works, and then the balancer is a completely separate circuit, rather than trying to bung everything on one circuit, which is what I normally do, and it just fails miserably. So basically, we want a buck boost converter with a low dropout, capable of some current, 3 to 5 amps, sounds pretty reasonable, yeah, sort of, I don't know, 20 volts would be nice. We can do 2 in series. It'd be really nice if I had an I2C interface, I2C if you prefer, so we can get some data off it, but that's not necessarily critical. So we want to sort by V in minimum, and we want this as low as possible. So that's looking quite promising. So 5 amps, 18 volts, so that gives us 9 across each cap. Right, I'll tell you what, that's looking pretty sexy, isn't it? I have a really weird definition of sexy, but let's have a look at that. You watch this being some retarded package. Oh God, we can get it in dip! Oh, you lovely, lovely thing. Or we can get it in a quad flat pack. Lefty. Efficiency. The burst mode is better than PWM, unsurprisingly. Well, actually, yeah, that's really poo on PWM. But I must say, the burst mode operation is actually really good. It's, in fact, that's staggeringly good. It's pushing 90%, over 90%. That's really, what a fucking package that is. Right, I think that looks pretty good. So let's see if it's on Fennell's website with a library package that I can download, and then I can drop it straight in rather than doing some dodgy rewiring of a standard chip. And no, it's not. And interestingly, why is it no? So that's been replaced by something. So I don't really want to use that. because they've only got 20 in stock. They're not going to get any more in. So if we like this design and want to make a few more, we've then got to go through the whole faff of redesigning the whole thing for a chip. Well, that's irritating, but we know this is sort of what we want. Let's have a quick look at the SEPICs. So, that goes sub-volt. Internal switches. Oh yeah, because we're looking at the internals. Is this... Oh, why did I kill my tab? UK Farnell. You can use Rapid, you can use RS. I just know how to navigate the Farnell website. It's taken me a few years. No longer stocks. Right, okay, let's chin that off then. So let's have a look at the SEPIC. So SEPIC, single-ended primary inductor converter circuit? Converter, I think it is. Don't really matter. It doesn't really matter. It's just the topology, so the way you do things. So these are only really going down to a volt. And these are much lower. And we've got one there that's a bit better. Very low supply current, 9 microamps. That's good. So that's going to reduce our losses. So that's the power to required, or the current required to actually power the chip that's doing the switching. That's pretty good. Switch current, 2.5 amps. Not ideal. It's monolithic though. Not that that's necessary. Just saves me soldering. So before I get too excited, why do I keep closing the UK Farnell page? Stop doing that. So page search. Available until stock exhausted. This is getting rather annoying. That's that. 1 volt, 32, 2.5 amp. Now it's the same one but with a number less. This will be the same. I'm assuming this is no longer stocked. Yeah, it is. Excuse me burning my lungs. Don't do it, it's bad for you. So these are starting to get in there. So if I put, so that's 1.6 volts there, dropout. I'm putting in a 2.5 volt cat, single 2.5 volt cat, you know, we're not going to be able to harness more than 50% of the energy stored in it. So, right, we'll chin off SEPICs. Let's have a look then. Ones with external switches. Sort by vmin. Oh crikey, these are even worse. That's annoying. I bet, let's have a look at the micro modules just for giggles. No, they're pretty bad, so that's not going to tempt me into trying to solder a BGA package. That's good, because they are bloody horrible. Might have to look at a different supplier. But unless they've got a buck boost LED driver. Now that could be interesting. These are likely to be constant current. Isn't necessarily probably 1.6 again. Oh, and it's a flyback. Oh, it'll do SEPIC as well. So that's in SEPIC mode. That might not be a bad show. Paste search. Oh, for crying out loud! Right, okay. Let's go with someone else. Well, let's have a quick look in Eagle, see what else we've got to choose from. So that was analog and LT. We've probably got TI would probably be the next one I would go for. So we've got Texas here. Let's have a look on Texas's website. Close enough. Smash the keyboard a bit until you get what you want. Products. And we want power. Do the Jeremy Clarkson thing. Oh, it'd be good if one of you fine chaps and chapesses would tell me a good one to use. I do have one at work that I could use a demo board, and I've completely forgotten which one it is. I could look through my order history, but lazy. Buck boost. I mean, inverting, we could do inverting. That doesn't bother me in the slightest. So inverting is basically where you end up with a negative voltage. But it doesn't matter for this because I can have two grain planes. It's not a problem for this particular experiment. So boost charge pump, I'd prefer not to have a charge pump because it makes measuring current and stuff a little bit harder. Non-isolated is fine. Where? No, don't. LED drivers are possible. Voltage reference, power management, special functions. No, I want to stay away from them. They tend to be complicated. PWM, a resonant one would be nice. So let's have a look at them. And buck boost. We'll have a look at buck boost first. The V in min 2.9, right? Okay, then we'll search for all here. We'll go V in min 370. I'm assuming that's milli. Well, no, let's not assume. 0. I call bullshit. Use my French, but yeah. Let's have a look at the data sheet. Let's tell you what, it'd be nice if we could use a standard circuit, so one they recommend in the data sheet, because it saves me thinking stuff. So here we are then. So 15 volts in on this example. We've got ground, so this is inverting. Ground's on the positive rail. Oh, that's a test circuit. That's what I'm confused. These are, see, the Linear Tech data sheets are bloody awesome. They are so good. This requires a bit more thinking. Standby current 15 milliamp. Jeebus, that's high. And it's PWM, so it's, I mean, they've got no efficiency graph. Oh yeah, they have. Sorry, I tell a lie. No, they haven't. No efficiency graphs on here. There's no suggested circuits. I'm just going to end up having a sense of humour failure. Let's see if I now stock it. Yes, that's a good indication. And these are in stock, and yeah, okay, right. Dip package as well. I must say, I've never used a dip package ever in my life. I know. Go figure. It's going to be the same one for both, isn't it? See, it doesn't even have the pin out for the different packages. I'm just going to assume it's the same as the dip. Oh, D or N package. Right, okay, yeah. Fine. No, I'm not getting a warm fuzzy feeling on that one. That's 3.6 volts, so that's just nah. Let's for giggles look at low dropout. These are linear regulators, so I'm not expecting good efficiency out of these, but you know, it might work. Good look at the Traco power actually. What are these? TSR? Oh, TSR 2450, that's it. TSR 2450. These things, I mean, they're quite expensive, but bloody awesome. They're bulletproof, these things are. Absolutely bulletproof. These are buck only, though, that's the problem. A minimum voltage. 2450s when I use for the 5.5 volt out. 6.5. Oh yeah, because it's a yeah. Because it's not a boost. Right. Okay. So right, this page isn't loading. I'll give it one more chance, and then I'll give up. No. Buck converter, buck charge pump, don't want boost, integrated switch. I wonder if a boost will do buck. Products. V and min. V and mat. No, they won't do buck. Really weird. I don't know why every boost converter isn't also a buck converter. It just seems, yeah, odd. Really don't want to do flyback. I can get away with it. Although at this rate we might have to. Right, okay, I'll give up with TI. Who else have we got that's potential? Oh yeah, Maxim. Well, we can't use that one. Oh, there's Worth. Well, Worth. I don't think they do chips. No. Let's do good inductors. There's Maxim. Am I going to get the Lads magazine here? Yeah, I am, aren't I? Oh, there we go. Products. Let me click it. Ah, clicking it too many times now. Oh no! Switching regulators. Ja, bitte schön. Buck boost. Oh look, this was straight in. This is our website. This is how our website should be. Everyone loves a good website. Recommended. So now let's just look at all. We want V in. Can I sort? Yes, I can. It's here. V in min ascending. Yeah, look, there we go. Good. You probably can't see this on your screen, so I do apologise. But when I find one, so 0.7 volts, that's good, but V out only goes up to 5 volts, which isn't a problem. 5 volts might be a nice test voltage, but V in max is only 5 volts, and we really need it to be sort of 20-ish. 42 would be fine, but we're down to 2 volts on the V in min. It's the same problem if we have a single cap under test, commercial cap at 2.5 volts. I mean, we're getting. Well, you got a different mouse this time. Come on then, drop it. Wait. Yeah, right, different mouse now. Come on then. And she's off. Okay. This is not looking fruitful, is it? I know they exist. Where have you put it? Oh, of course you've put it just out of reach. There we go. Come on then. Come on, Pippa. Oh, International Rectifier, do they do? What bloody heck? I ain't soldering that. Linear Maxim Texas worth. I'll tell you what, right? Let's get something on a page. Let's at least get some designing done, and then we can come back in and we'll put a placeholder in for a voltage. Excuse me, a voltage. We could use an LM317 and then just control it. Variable resistor. Digitally controllable variable resistor. That's probably not a bad shape. A bit more complicated, but I can stick a little Arduino on the board. What am I looking for? Wago is what I'm looking for. I'm not seeing Wago. Have I not enabled the library? Library. Oh no, I know, because they're not under Wago, they're under Con Wago, that's it, that's what I want. 2-port. Love these little connectors, they're bloody awesome. So what do I want? Okay, so I want power in, I want power out, click, okay. Let's use the text command, so power in, click, power out. Okay, right. We have something on the page now, that's promising. Let's set the design at 2 caps. Okay, so cap 1, cap 2. Text, so cap 1, cap 2. That should say cap 0 and cap 1, but let's not go there. Okay, so we've got cap 1, cap 2. Let's not put a Xena across it. Well, we could do. I'll tell you what we'll do. We'll put a Xena across it, and we'll put it on a switch. Diode, standard Xenas. Let's use. Right, let's not. Search in Eagle. Utterly diabolical. Oh, they call it a Z diode. Yeah, per diode. Xena. See the Xena. Why didn't it come up in the search? It's a poo. I don't know. Yeah. It's going to need to be beefy because it's probably going to need to take a bit of current. Particularly if I'm farting about it. So, well, let's do that for the time being. So we're going to have a protection Xena across each. And then I want to turn these off. So we want switch. Still switch should do. In fact, no, would a dill switch do? They're a bit annoying, aren't they? Yeah, no, let's not use dual inline. Let's use cheap as beans, aren't they? Oh, but it needs to be a latching switch. No. Oh, come on. I need to make a list of the switches I like and use on a regular basis because I can never bloody find them. Any suggestions? I'm just looking for one that isn't mental large. I feel the cat just like pawing my leg. So I want on or momentary. No, I want on off. You're right, that'll do. Hello, Pepper. So that will probably do. So what's that? On, off, on. Well, let's get some wired in so at least we can see it. We can play about with it. Xena goes through there. That's going to be the common. So that then comes back down to here. Okay. That's the sort of theory of operation. So now, right, if these are 2.5 volt Zenas, for example, we can protect it with that. Now, there's no reason why we could not extend this theory. And do something like this, right? Okay, where 2v5 here, yeah, and then Xena, I don't know, say, well, I don't know, let's do 6v5 for argument's sake, because there, and then what I can do is go highlight, copy group, and click. That they actually connected. Right, and then we can turn these on and off as we see fit. And actually in this configuration, you could put a 2.5 volt cap in cap 2's position and a 6 volt cap at cap 1 position. You could do that. The problem with this is you've only got these two voltages, or however many times we copy this out. So to show you what that looks on the board view, this is how we get the components. We can drag and drop them in. But let's not do that just yet. Right. So let's get some ground planes and stuff going. Supply, let's go with ground. But we should do 0 volts really. So we'll have a 0 volt there, power at 0 volt there. 0 volt comes in there. These two nets join. Power in can go straight to that. We can have another switch. I mean, this is getting a bit silly on switches here. I do appreciate that. But we're getting the rough idea of what's going on. There we are. So we can then, connect this. And we could do the same on the power in, but it's easy to yank a cable out or disconnect the load bank. Power supply, sorry, power supply. Okay, so let's have a look what this looks like on the board. So X1 is power in. So let's have that at the top. Let's have X2 was power out. So let's have that up there. So they're separate. Cap 1, Cap 2. So Cap 2. Hang on, what's that? X4 is Cap 2. Closest to ground. And these can interlock. I mean, I can move them about later. We've got diode 1 and 3 goes across X3. So 1 and 3 goes across X3. So really these want to be sort of like that maybe, with switch 1 and switch 3. Switch 1, switch 3. Just do a rat's nest on there. Switch 3 goes sort of something like that. Switch 1 does something like that. And do a bit of a rat's nest there. Now let's get a ground plane. And then I can name that 0 volts. So now that should fill that in. Yeah, lovely. And we've got the thermal pads and stuff. That's good. Let's get some of these in. Probably wasn't any quicker, was it? And go a bit close to the edge. This is just sort of testing the idea out at this stage and just seeing what it will look like. This design's clearly going to evolve somewhat. So a couple of switches here. We can nest that. We can connect some stuff together. I'm in Mills here. In Mills, but never mind. I could do with these being a bit beefier. There we are. And these will end up on the underside of the board actually, but if I make this single-sided, makes my life a bit easier. So clickety click. That gets connected there just so it's a bit more visible. That goes, where's that going? Oh, switch. Switch 5 is on the output. Oh, that makes a bit more sense. Rat's nest. Here we are. And that goes down on there like that. This one actually comes out to here. go. Oh, hang on. Schematic's gone a bit crazy. Right, give me a sec. Knew something didn't look right. There we are. And that can come down in there like that, something like that. Right, this is just quick and dirty, quick and dirty. So that comes over to there. That looks sensible. There's our output switch. So let's have the output switch like near the output. Sounds logical, does it not? And then let's have this coming down on there like that. So this would work for 2 cases. Not ideal. But we still need a regulator. So let's switch back to this. So the output needs to be regulated. So let's do that. Still need a flipping regulator, don't we? What's under VReg? No. Have another look at linear. I'm sure they do one, I'm seeing it. Linear, here we go. It might not be one of them. Into that one. Op amps, CMOS. For buck boost. Voltage refs, audio amps, power op amps, no pumps, op amps, comparators, PWM. No. We could be naughty and just use an Arduino to program it. Not really quick enough. I mean, I could take the piss and use a DSP, but I've not done any DSP stuff for ages, actually. That could be quite good fun. You might have to use one of these discontinued things, you know. I'll tell you what, right? I'm gonna have a quick break. I'm gonna make myself another coffee because that's important. I'm gonna crawl through the linear website, well, analog website, and see what I can find, and I'll come back. I don't know, half an hour or so, whenever it is. I mean, these videos will be going onto the channel anyway at some point. When they've converted and YouTube's done the doings on it. So if you're not free to watch what hopefully is the second half and the final half, then not to worry, you'll get it all. I mean, it's an LGA, isn't it? It's a landing grid. That looks reasonably sensible. Why is there two chips on one? That's pretty cool. That's really cool, actually. I quite like that. It's not what we want. But yeah, anyway, so rambling. Give me half an hour or so, and then I'll be back on, hopefully, with the right chip, and we can continue this Supercap project. So yeah. and grab yourself some lunch, and I'll see you shortly.